So this session, we'll look at the how cybermarine fits into the wider research landscape. We have 5 presentations and they are 10 minutes each. First one up is Dr. Suzy Black. She's a senior scientist here in Nelson and the program leader of another MBIE research program called Reimaging Aquaculture. Many of you know Suzy very well. It's on to you, Suzy.
Thanks, Ivan. I'll just try and do the old screen share. And we'll get into this. Yep, kia ora koutou. Thanks, Ivan. I'm Dr. Suzy Black here at Plant and Food Research, and I'd just really like to thank Sue for extending the invitation to me for this. It was just a really great opportunity to show everyone that these projects certainly aren't done in isolation. I'm definitely coming at the sort of raw material end of things, so sort of further back from the processing side of things, but this is going to be a pretty damn quick whistle-stop tour through some of the technologies that we've developed over the years at Plant and Food around growing, harvesting and handling systems in fish. Sort of been over the last 25, 30 years. I can make the slides go. Great. So I'm going to look at 3 sort of different technologies that we've developed, and they sort of cross over from aquaculture through to wild fishing. The first one's going to be rested harvesting with Aquaculture. Next one is precision seafood harvesting, and then on to our latest program, which is reimagining aquaculture and the mobile production systems in aquaculture. But I really want to talk first about the commonality between all these, and this is very much a fish-focused approach to our research. And what do I mean by that? Well, before we get to that, this is all about the holy grail of control and consistency, which I know is pretty dear to your guys' heart, and this is where it all happens with the raw material. And if you don't have control and consistency, I know you guys know all about the problems with that. So over the last 25 years, our group has spent a heck of a lot of time looking at how to make the most of what we harvest, but we also have started looking at how to make more to harvest. And everything is with that underlying focus on fish-focused design. So what is it about fish-focused design that's a bit different? Well, we're a bunch of fish physiologists, and so our focus is very much on the whole animal, and we'd like to bring everything back to what the fish needs. So what does it need to be at its best? That's what we're really here about. And rather than building a process and then stuffing the animal into it, we're very much about looking at the animal and fitting a process around the animal. So just getting onto these 3 different examples, and as I mentioned before, they sort of span aquaculture and also wild fishing. So into rested harvesting with Aquaculture. Back in the early 90s, salmon farming was very much a fledgling industry in New Zealand, but they had quite a lot of quality issues. And this was linked very much to the harvesting process. It was pretty violent. And the research team really wanted to see if they could take that intense exercise component out of the harvesting process and see the improvements they could make. Just got a wee video here, and you can see when it starts that the harvesting process was really quite violent. There's a lot of movement there, lots of fatigue, exercise, and damage was occurring. But the research team wanted to see if they could take all of that out of that process, what you can be left with. And through a sort of period of R&D, they found the best way to achieve this was through using a food grade anaesthetic, Aquaculture, and that gave the best results. And sort of this video is a bit chalk and cheese. The fish are in the anaesthetic bath here. They basically swim around until they sort of fall over and go to sleep. It's very gentle. You can see that the exercise is being taken out, the damage is being taken out, and the fish aren't as fatigued. And so what are some of the benefits of rested harvesting? Well, taking out all that damage and exercise, you definitely improve the fish welfare. And I know we're talking a lot about the food component here, the fillet component, but you can imagine very much so for the whole animal. For 100% utilisation of the fish, it very much improves quality and consistency of the fish. And so energy is retained in the muscle and delays rigor mortis. And you get much better texture, fillet quality, less blood spot and bruising, and less gaping. So we were left with the glaring question. Once we'd been in aquaculture, a really controlled environment, we started thinking, well, how do we apply those concepts that we learned from aquaculture to the wild fisheries? It's much harder prospect to go from aquaculture to wild fisheries. And at the time we were looking at hoki. And our focus wasn't initially on harvesting hoki, but improving post-harvest quality. It soon became really apparent that the condition of the raw material, so the state of the animal coming up on the deck of the boat, was a real issue. And once again, that lack of control and consistency was really governing product quality. And we needed to start looking at where that damage and fatigue was occurring prior to the fish coming on deck. And it wasn't until we got cameras down into the trawl and we could see what was happening. And just another video here, and you can see the hoki really packing into the back of the toe of the cod end here, but you can see that there's fish in front of that are swimming normally. And this is sort of was our real aha moment. It's like, well, you know, why do you have to strain your fish out while you're catching them? Why can't you create that environment for the fish to look after themselves? And that really, really directed our design for what we did next. And that was taking the physiological tolerances of the fish into consideration. And we started looking at matching the velocity of the water inside the trawl to the swimming speed of the fish. We wanted to minimize turbulence so that you didn't get the tumbling, and so fish didn't collide with each other or with the trawl gear. We were really, really about giving control back to the fish during that harvesting process. And so this led into the research program, Precision Seafood Harvesting, which we conducted with Sealord, Sanford and Moana, New Zealand. And just to give you an idea of what was happening inside the trawl environment, this is a bit of a compilation of a number of videos. Oopsie, sorry, I've moved one on too far. We'll go back to this one. This is just a footage of a conventional cod end in the inshore fishery. You can see the tumbling with inside the cod end. This is a mesh cod end, so you can imagine the abrasion and damage, but inside the modular harvesting system, you can see the water velocity has been slowed down. The animals are able to control themselves. They're not bumping into each other. They're not creating blood spot and bruising and gaping. And they're very much looking after themselves. This is in the deep water fishery, again, back in the conventional mesh cod end. So it's quite chaotic in here. You can see fish coming in, but as it'll cut to the modular harvesting system shortly, and we'll see that the fish are, sorry, this is still in the mesh trawl, again, the video from before. The fish are fairly moribund, but in the modular harvesting system, here's hoki that are able to swim and look after themselves very well in the trawl, to the point where here's a hoki that can turn around and smile for the camera. But you can see, and this is probably one of our most favourite videos from the program. This is Alfonsino down the trawl, very much almost swimming like wee snapper, but you can see that control is being given back to the fish. And so how does this relate to once these fish come up on deck? Well, this is quite different for the guys coming up on deck. They're used to more less lively fish, if you like. This was quite a surprise for the guys, and you can imagine it introduces some health and safety issues with wriggly fish. But you can see the difference in quality quite clearly compared with the normal fish coming up on deck. This is Alfonsino coming up. The guys actually thought this was a different species of fish. They're not used to seeing them with the silver side. They normally come up and they're completely orange. But you can see, again, this is inshore trevally. Just the difference in quality coming up, and they're just absolutely stunning fish. So just recapping, the fish quality here is the name of the game. Very much idea of landing the fish in water to minimise the damage and reduce fatigue. And it also, although this is not necessarily a processing concern, but there's that greater survival potential of undersize and incidental catch from fishing. And there's other positives here is being able to do long tows without compromising fish quality. So just stepping back to this picture for a moment, and although we've spent a long time of looking at how to make the most of what we catch, we've also more recently been looking at how do we create more to catch, so increasing productivity, but we've also been looking at this with that underlying theme of fish-focused design. So we stepped back into aquaculture here, and we started to think about, well, how can we bring a more fish-focused approach to aquaculture production? And we came about this, and we really wanted to turn traditional static intensive aquaculture, so aquaculture that sticks in the same place, on its head. And we came up with a concept of going mobile. And the idea around this was a mobile production system out in the open ocean, so open ocean aquaculture. So we started thinking, well, what could this look like? Well, I knew what it wouldn't look like. We're tackling this from quite a different perspective compared with probably the rest of the world. Some of the overseas approaches are heavily engineered to withstand the harsh open ocean environment. They don't move, a lot of them, and so they have to withstand the environment year round, much like our conventional inshore aquaculture does as well. Our concept was to go mobile, but also take a soft engineering approach to this. Part of the design criteria for this, although, you know, proof of concept, is to take not only a fish-focused approach to this, but also a whole of ecosystem approach to this. So when we're developing the technology. So if we're going to be putting a production system into the environment, we really want to make sure that we're looking after that environment that we're putting the system into. Because of our enormous exclusive economic zone in New Zealand, there's the opportunity to significantly increase production in our territorial waters. The mobility aspect's an interesting one. We see there's a lot of advantages there, and one of them is around resilience, and not only resilience to potentially climate change, so you can move these systems to where the fish will be at their best as far as temperature goes. It also potentially opens up opportunities for species diversification. It also opens up opportunities for biosecurity opportunities too. So some of the key design principles there for us is obviously that fish-centric design is understanding what are the innate behavioural preferences that fish have, so looking at flow and temperature, but also optimising the culture environment to the size of the fish and also the species. As I mentioned, we want to work with the environment. We want to utilise the power of the ocean rather than trying to fight against it, and take a soft engineering approach to this challenge. It's that very much that whole of ecosystem approach we're taking to the sustainability, and very much part of that is having a very light environmental footprint. And we think there's a potential there to lower the cost and reduce barriers to implementation for this type of production system. And we think there's potential there for it to be scalable. So the concept is very much to develop a flexible, mobile and tunable system that could really utilise New Zealand's open waters and support those optimum conditions for different species and life stages of fish year round. And so the mobile nature of the technology allows for constant optimization of the environmental conditions, the water quality, and really allows production of high welfare, healthy, resilient fish. And I need to point out, this is very much a proof of concept research program. At the end of the program, we're not going to have an 0800 number where you can ring up and order your production system. We know it's very ambitious, but the team very much believe that it's our job to demonstrate what's possible. And the next step is then to develop the knowledge and the tools to turn these possibilities into a reality. We're right in the middle of this research, particularly around understanding the fish. Got a couple of exemplars here. We're using snapper and Chinook salmon, and we're also developing and testing prototype fish enclosures. And hopefully within the next year, we'll be able to test fish within these prototypes as well to get an idea of have we designed and created these fish enclosures that the fish like and are happy to be in. So of course, we're not in isolation. We've got a huge number of collaborators and supporters for this program to be successful, just to give you a taster of who's been involved. But I'd just like to finish with this conclusion of these sort of big sprint through these three main technologies of rested harvesting, precision seafood harvesting, and mobile production systems. And that's very much the focus of looking after your fish and they will look after you. And whether that's whether you're creating fish fillets for sale or you're looking at processing and 100% utilization of your fish, I think it's a pretty good take-home message for everybody. that's me. Thanks very much, everybody. Sorry it was such a sprint, but any questions, please fire away at the end of the session.
Yep, I'll just write them in the chat. Thanks, Suzy.
No problem.
Right, so next up, you have seen him before. It's Dr. Hemi Cumming. He's our research chemist, as well as part of the PFR's Māori business development team. Hemi will talk about, he will showcase our student outreach program. Over to you, Hemi.
Okay, ka pai. Kia ora tātou. So as Sue mentioned earlier, as part of this, as part of the broader program, there's a great opportunity to do some outreach to support, I guess, science, the pipeline.
Excuse me, Hemi, you need to change your...
So yeah, interest in outreach and in particular, a great opportunity to support, I guess, Māori pipeline into science, into the sciences, as we, as we found out when we were at the early stages of designing the program, but not very, as we know, the movement of Māori through the sciences isn't high. So this was a great opportunity, not only to think of some ways, and we pushed it back because we couldn't get sort of the postgrad students into the program, but a great opportunity to provide some activities where we could expose some students to research, opportunities to meet researchers, and learn the possibilities within seafood research that's going on, and most of all to get a bit of a hands-on experience, to get their hands dirty. So yeah, there's 2 areas that we and these are still in progress. These are still things that we want to build on. But yeah, 2 areas is at the high school level. We're working in designing sort of activities and sort of experiences, and then we have some studentships, which is really amenable to university students. So we designed some activities. A bit of a shout out to Ivan, who designed some activities around the digestive enzymes, and Alex Leonard, who's one of the PhD, working on a PhD within Cybermarine, who pulled together a collagen activity, and a few of us who worked on the dissection. So these were just some of the activities that we thought might be fun, but also really aligns with the program. So we ran a trial. We were lucky enough to have Mark Chamberlain, who you can kind of see looking very enthusiastic about to cut up a fish, who was part of a Royal Society teacher fellowship, who kind of helped us understand how we can be a little bit more engaging with high school students. So here with some photos from one of the trials where we had a bunch of students that Mark pulled in. But here they're dissecting, they're chopping up fish, they're getting an idea of what parts make up a fish, and by sort of weighing things, they got to get a real good idea of how much is fillet and how much other bits and opportunities there are in byproducts. So they took a little bit of the gut. They took a little bit of the ceca, which is, I guess, the enzyme producing gland. And so they got to kind of get a play and see how you might process it, and then how they behave. So we have here, they were playing around with milk and proteases and lipases. So you get to see that curdling, and then a few lipases will kind of give it a real strong cheese smell. So just sort of fun activities, but really gives them an idea of what enzymes could be, how they behave with materials, and then obviously a more technical understanding using a UV spec. Here's them playing around with collagen. they took the skin and got to see how you might take a bit of skin and then treat it with acid to then provide kind of a purified collagen product or collagen material. And this was just followed on with sort of demonstrations where they could see how this fish skin went on to be purified and then into sort of, I guess, experimental testing. We have these 3D printing of collagen, and then we have the active layer. They got to trial that out and get a bit more youthful than they already are. So the summer just gone, we had Georgia Patching. So she's Ngāti Kaupata, which is in fielding, but she's a student of Massey University. So in collaboration with the Puhoro STEM Academy, which is, I guess, an academy which is really boosting Māori into the STEM sciences. We co-funded her fellowship, her studentship, and she got to do a project over the summer. And her project was all about taking some of these fish materials. She got to have a play and blend them up, throw some surfactants in, and then just see, and then extract the oils from the surfactants, and then experience, I guess, all the ways you will analyze and process these things. So she also got to sort of pull it all together into a poster and present it. So a really cool opportunity and experience to kind of see a mini project of something that is really interesting and new, and get hands-on. So that was really cool. So I guess just moving forward, we'll be trying to expand these. Essentially, we'll be wanting to bring more people in to do hands-on activity days from schools. We sort of can only really take we sort of take just probably like 4 to 6, because we really want to make it a real interesting and great experience. And then there'll be future summer studentships. So yeah, these are all kind of, as I say, all in the process, and we sort of are in the process of kind of like exploring students and who might want to collaborate and bring on. And so yeah, there's a little bit of an open invitation. So if you have any ideas or students or keen to collaborate in this space, we are certainly interested in those conversations. So with that, I'll just send a big mihi, acknowledge the students, and you know, he looks super happy here, and yeah, we hope to have future students. Kia ora.
Ka pai, Hemi. That is excellent. Right. Our third speaker is Anna Yellop. She's the General Manager of the Bioresource Processing Alliance. Over to you, Anna.
Thank you very much. Can you see my screen all right?
Yes.
Great. So some of you will know me with my Seafood Innovations Limited hat, but today I'm here with my Bioresource Processing Alliance, or BPA, hat, which I'll talk about today. So the BPA is funded by the Ministry of Business, Innovation and Employment, and we're all about taking biological byproducts from the primary sector and turning them into high-value products, preferably for export. So if there's anything that you see here today in terms of the research that's going on that you'd like to look into further at the sort of commercial end, that's where you might be interested in talking to the BPA. So the parties that are involved are AgResearch, Callaghan Innovations Research Division, Plant and Food Research, Scion, and any New Zealand university as well. So basically, we undertake R&D projects alongside industry to help develop those products. So companies or processes as well. Companies put in co-funding anywhere from about 25 to 50% cash co-funding, and we undertake the projects on behalf of the company based on very applied ideas that the companies want developed. And we also do student projects as well. So obviously everybody knows that the whole point of doing a lot of these things these days is about environmental responsibility, but I also take the view that it absolutely has to be viable from a commercial perspective. It's very hard to get buy-in at a company level, even if there's people within the company who just see the environmental side of it. It has to work for the company in terms of economics if you're working with byproducts. So for us, we ideally make money and save money for companies, but if it can at least save costs for companies, we're pleased about that. It's been particularly interesting from my perspective over the last couple of years because of COVID, because this has kind of brought forward as a priority a lot of byproduct use for companies, specifically around things like trying to get products to market, shipping challenges, short shelf life products, markets turning off overnight that because of restaurants being closed, etc. People putting all their eggs in one basket in some cases and not having enough variety. So it's particularly interested at, I guess it's coming for people whether they like it or not to do have a variety of opportunities coming out of their primary products. So some of the reasons you might be interested in looking at doing these kind of projects is it's a chance to collaborate if you're interested in that. Doesn't have to be collaborating across companies, but it's collaborations across research organisations is a useful thing. We try and pull together the best teams from wherever the organisation is, and it doesn't have to involve collaboration, but ideally it does. So a lot of the clients that we talk to are interested in health trends, particularly out of COVID as well. So in the fruit and vegetable space is a really hot area in terms of people wanting to avoid getting sick in the first place rather than necessarily feeling better once they are sick. So you're in a really good space in terms of aquaculture and seafood generally, because there's health benefits there. UFA stands for the Upcycled Food Association, which is an interesting thing that's come out in the last few years about educating consumers about the benefits of using food from byproducts or any product from byproducts, and just about getting people to realise as we say, it's not about stuff that's swept up off the factory floor. We're talking about perfectly good material that's perfectly nutritious. It just might look a bit funny, or it might be a different part of the raw material that maybe doesn't look so appealing in some form. So just trying to get people to realise the benefits of having byproduct use in their ingredients and products. So for some companies, again, it's that having a range of products is useful these days, especially if you're in a seasonal game as well. So going back to horticulture, they have a very tight time frame for some harvesting, of course, and so the thought of doing something with the byproducts is way out the window at that stage. But when the season is over, if you can do something with your byproducts and get value at the processor or grower end, that's a really good outcome. It's also hedging your bets so that you're not so tied down to one primary product if things go pear-shaped for things like COVID or shipping challenges or container use, etc. Again, it's obviously a real appeal at the moment to take a whole of resource approach. Sue mentioned it earlier about using everything that you've got, basically, not wasting anything. And if you guys can recoup as much value at the industry level from the stuff that you've paid to harvest or grow, then you should do that. For a lot of companies, it's about getting higher value from their products as well. So moving products up the value chain, and that's not for everybody. Some people are quite happy doing just something their business as usual, which is totally fine, or just a little a nudge above that into maybe ingredients or something like that. We're not always talking about really high value pharmaceutical type products as well. So we can also make lots of introductions to parties. We've got parties who would would like to use your raw material. We've got parties who have raw material that like someone else to do something better with it. So there's lots of opportunities for people there. And of course, if we can help reduce emissions from the way we process things, you're not carting waste product effectively around the country to not use, that's a benefit for everybody. Just a couple of examples of things that we've done. This, you guys will obviously all be familiar probably with Omega Plus, which is New Zealand King Salmon's pet food division. So a few years ago, some of our researchers helped develop some of the treats, the pet treats, looking at the palatability, getting the recipes right, making sure the pets liked it, etc., and coming up with various recipes. So that's been a very successful product as far as we're concerned, and it's been a great relationship with King Salmon. This just shows you some of the other variety of things that we do, so or have done in the BPA. So fertilizer is probably the lowest kind of value, as it was mentioned earlier. It's kind of increasingly a bit more diverse, but it's at the low end of the things. You've got collagen, that's all the rage at the moment, I'm sure you'll appreciate. We've looked at shellfish, of course, into a range of products, including pharmaceuticals. We do fish oils, etc., for a range of ingredients, foods, nutraceuticals, supplements. Seaweed, I'm sure you'll all appreciate, it's very hot at the moment as well. So we work with nuisance species and secondary streams as well in the BPA, because again, we're talking about not the primary product, but a secondary stream. And obviously we've done pet foods, and we've been looking at bio-based composites as well from marine species. So just, I just want to touch on a couple of things that we have learnt along the years about working with byproducts. So securing the raw material is really important. If you don't have that raw material but you want it from someone else, don't do your business case on not paying anything just because it costs someone to get rid of that byproduct currently doesn't mean they're going to give it to you for nothing. So you need to be realistic about what the value is of that raw material when you're buying it. Equally, if you've got that raw material and you're selling it for $1 a kilo, it's suddenly not worth $90 a kilo because someone wants to make something a little more valuable out of it. You've got to be realistic between the two parties on the value of it. It's tricky when we're talking about byproducts. So core products obviously get the headline for companies, unless you're in the business of always making products from other people's byproducts. Having your core business focused on is always the way it goes. So getting a product to market is tricky in the first place, but with byproducts it's even trickier because they have to get to market and then stay in market, and that's sometimes a totally different marketing team and different costs, different pathway to market, different customers. So those things shouldn't be thought of too lightly. Also, before you do projects, think about your appetite in your business to put in infrastructure if needed to develop these products or processes at scale, because no one wants to spend money doing projects if no one's going to actually execute on them in the end. So just be realistic in your business about whether that's something's going to happen. A lot of our clients really like the fact that we undertake the project management of these projects on your behalf, because a lot of these projects are ideas that you might have thought about for many years, but just haven't had the resource or energy or money to do yourself. So that's the beauty of getting us to do these projects on your behalf, but very much driven by what your requirements are. It's not going off on a tangent doing something random. Again, we've got the connections that we can, if you don't know where to start in terms of what you'd like to do, we can make lots of introductions to parties, and I'm not affiliated with any particular organisation, so feel free to contact me and I can find a range of people who could help with any projects that you're interested in. New Zealand always has these challenges at scale, right? So we can do a lot of work at lab scale and pre-commercial scale and even commercial scale. But again, making sure there's going to be money to put in equipment if you need equipment. Like, we'd rather not have you having to spend money on putting in new plants if we don't have to. So we'll work with what you've got, but just be realistic about that. And finally, we just think about the beauty of using the BPA is that we share the risk with you. So we tend to put in more of our money at the early stage projects to de-risk it for you, so that by the time we've done quite a bit of work on it, you know it's going to be reasonably likely to work, and then you can put more of your money in at that stage. So that's pretty much it from my perspective, and feel free to contact me if anybody needs any help with anything. Thank you.
Great. Thank you, Anna. We now have Dr. David Aitchison. He's the Research and Innovation Manager at Trinder Engineering, who are based not very far from us, just in Richmond. David.
Do you have my screen there? Can you see that?
Yes, if you just go into the presentation mode.
Yep, let's try that.
Excellent.
Yeah, we should have that. Right. Okay, look, thank you very much. And I'd like to thank Anna as well. Gave me a very nice introduction, in that I'm going to talk a little today about summer internships and how they can drive collaborations. And in the summer just gone, we drew on some funds provided by Anna through BPA in collaboration with Cybermarine to provide solutions into the research program there. So first of all, who is Trinder? What do we do? I mean, we're an engineering firm. We're actually a family-run firm with 100 staff. Been around for nearly 70 years now. We're based in Nelson, so it's really handy to work with people like Susan Marshall at Plant and Food. And we are a company that's spread across 3 different workshops, working primarily with primary industry, but we also get involved in very specific solutions for individual companies in special purpose machinery design or special equipment design by and large. We have a dedicated design team, and we also have research and innovation facilities, and can take product from idea right through to finished solution. So within the company, we have dedicated staff naturally, ranging from trade staff right up through to professional engineers who've come through education systems offered by obviously universities. But we also draw on students, and we invest heavily in that, and that's perhaps where I come in more significantly in the company, in that my background is from an academic foundation. Currently, I'm the Research and Innovation Manager, and by drawing on the students and giving them experience in the workplace, we can also help support local industries. And that's a case study I'll talk about today, in fact, and just walk you into that right now. So I am involved in the Cybermarine program, as mentioned, along with Trinder, and supporting Sue in the industrial side of that. But one particular conversation led us to understand there was a problem that Sue and her team had that wasn't on the critical path, but would need resolving so that they could move forward with their research as they moved forward. And this was the introduction of a window into their processing plant to allow for laser spectroscopy. So they needed some sort of near-infrared windowing facility that would allow product to flow beneath it and allow them to obviously develop their sensor systems and analytical systems to observe the product as it flowed past. And also not introduce things like stagnation or pockets of gas gathering within the processing stream. And that sounded to us very much like the sort of business we do, which excited Sue Marshall and the team, because it's something that they just didn't have the immediate resource or time to look at. The problem we faced was finding staff to do that, because it was a fairly labour-intensive undertaking, or so we perceived it to be, and to allocate professional staff to that really wasn't viable. And that's where Anna came in with BPA, and with some discussion there, we identified that we could secure some internship funding. And naturally, we, through our previous experiences, knew how to interact with the University of Canterbury and draw in students from the engineering department. They're one of the mechanical departments at least. So the stage was set basically. Once we'd agreed the funding, we'd identified a project, and it meant that we as a gathering could work together and develop new linkages. So that was across BPA, ourselves at Trinder, the University of Canterbury, and of course the key player was Plant and Food Research. So the project, we saw the benefits, certainly for us, and I believe for the wider team, is that we can build relationships locally or even nationally to help support, in this case, the aquaculture or seafood harvesting side of business, and also sharing the knowledge and skills that existed within that group to produce physical prototypes or even commercial pre-production prototypes, if that's what's needed, by pulling those skills together. And certainly as an engineering firm, based on projects that we run, I mean, we run a very diverse range of projects up to multi-million-dollar solutions. Planning is, of course, crucial. And that was the first step we took. And it was warming to see that Anna specifically mentioned that in her prior slideshow to the one I'm giving now. So we engaged with the team, identified various stages and steps in the project, and put together a project plan, which was quite crucial in this particular case. And it's something I'd strongly recommend, even though you're dealing with what seems to be a very short-term project, in this case of only 12 weeks, because there are a number of players, and because in our case it was over the summer when people were sort of migrating in and out for Christmas breaks and the like. The planning was absolutely essential, and particularly down to the fact that we wanted to get a prototype out into the field and tested, and actually had suppliers to deal with and manufacturing to contend with as well. So planning is absolutely crucial, even though these projects are small and maybe low budget. Okay, and this is what we do as daily business within engineering anyway. We identified the problem. In this case, we identified that we needed a near-infrared windowing capability that would intersect the flow of processed fish. And we introduced the team to a formalized design process, and that's something that I'm quite familiar with. In fact, I taught it for some 17 years at Canterbury. And so we identified these stages, which you may, if you had sharp eyes, you'll have seen that in the process plan in the previous slide. And most people, when you immediately talk about design and finding a solution, jump straight to the illustration you can see there in the lower panel with sketches and think, all right, we'll grab a pencil and a bit of paper and away we go. But in fact, in a formalized design approach, there are a number of steps that must be taken before you engage with that. And that's crucial, particularly in a team environment where you get a number of people playing into that solution, and all with valid ideas and also knowledge. So after a rounded literature review to see what other offerings there were in the marketplace and what technology transfers might be possible, we formulated a design specification, a product design specification, and that's what guided the work as we moved forward. We then engaged in our sketching and creation of ideas, and being a design office, we had the benefit of a number of fairly seasoned engineers from within the company, and so we sprung the notion of what we wanted to produce to them and captured their ideas, and actually then we're able to model those up in a 3D solid modeler. And you can see a couple of illustrations there captured from the screen. One of the solutions in the top view there is an isometric, and then a sectional view so you can see the internals of the simple product that we came up with. So that's one solution. And it was very helpful to model up what we thought were the best ideas and then share them with the team at Plant and Food and let them offer feedback and commentary so that we could take those ideas on board and then try and redevelop those and engineer those into the solutions we had, so that they were actively involved in that design process and the solution selection. And that's also where the planning came in. You know, it's really crucial to know when we would be available and when we'd stage meetings, and so that the team knew what they would get and when they would get that. Part of the support that Plant and Food offered in the process of coming up with this final solution was substrate testing. So we needed to know certain properties of the material being processed so that we could model that and look at how it flowed through this device that we were creating, to ensure that we didn't introduce problems of stagnation, isolation of certain materials, or segregation of materials in the stream. We did some computational fluid dynamics. And we'll just move on and look at that. A couple of the features just before we move on from this, you can see how streamlined the tube is in the bottom illustration in the right of the image there. And that was a design we came up with to ensure that nothing got in the way of the flow. And the windows there are removable for easy cleaning. So this is the flow analysis. It was conducted on a piece of software called ANSYS, quite an expensive bit of software, and one that needs quite specialized skills. We do have those skills as it happens in-house, and certainly the student that came and worked with us had some skill sets, but would further develop those. And this allowed us to look at how effective the unit was at not disturbing the flow of the product. I won't dwell on that too much, but just to say that once we've got the CAD model generated of a solution, we can then create added value by doing quite deep analysis here. And that was supported by the data gathered by Plant and Food. And that helped us validate the solution before we went ahead and made a physical prototype. Because of the complexity, we made a 3D printed part. You can see that in the left image with the various pieces. The little square part is the part that the near-infrared window sticks to. And we bonded that with silicon, introduced it top and bottom of the body of the unit that fits into the pipeline, allowing inspection either from above, below, or as a transmission type application. Integrated RJT fittings, and that was at the request of the team at Plant and Food for easy implementation. And you can see in the right image there the product actually in use, and you can see the material actually flowing through it. So the translucency of the material brought significant benefits over this being made in stainless steel, for example, which was our original intention. So a number of benefits there, and the opportunity for the team to actually trial this in situ, and we can implement other refinements as we move forward. So in summary, look, this was just one of a number of summer intern projects we've run as an engineering firm. It's our way of reaching out to a community, to an industrial sector, and trying to build relationships, provide knowledge and expertise that may or may not exist within the firm, or certainly broaden the capabilities there and combine. A few lessons we've learned is that you really need to get on the ball early. You need to recruit students very early in the year, maybe April, May. Otherwise, there's issues at getting good students. Having support from people like the organisation at BPA is crucial. That really does help, and thank you, Anna, for your support in that process. And also really just building those relationships with across industries. And the internship is quite a cost-effective way of getting quite a stiff number of hours, a large number of hours into a project without it being swamped by cost of engaging professional engineers directly. But for example, in our case, we could sort of supervise a student and keep them on track. So it seemed to work well. And just before I close, you know, it's something I'm passionate about and something I'm pushing towards. And certainly with Nelson Regional Development Agency, we have a vision of a centre of applied ocean engineering research developing in the region. And I hope to see that take root. It's certainly, the wheels are already turning, and there's very good support from a number of players in the region. And it's something that could support the country on at a national level. So I don't actually have my clock apparent here, so I'm not sure where I'm running on time, but I'll wrap up at this point just to say thank you to you all for listening. This was just a case study. I know a number of people do engage with interns and postgrads, and I'm just saying this is just a slightly different way of looking at it and a case study to illustrate that. So thank you for your time. I'm happy to answer questions when the time's right.
Yep, thank you, David. I'm sure there will be a couple of questions. Probably we can leave those towards the end of the forum. So
thank you.
Let's move on. Our last speaker in this session is Professor Colin Barrow, Alfred Deakin Professor and Chair in Biotechnology at Deakin University in Geelong, Australia. If you can just stop sharing your screen, David, that would be great. Thank you.
I'll share my screen. So can everyone hear me okay?
Yes.
You should be able to see the presentation.
Looks great, Colin.
So I'm going to talk about some of the things that are going on in Australia. You might notice from the accent that I'm actually from New Zealand, and I've been working with Sue for quite a long time, and I'm very keen on collaborations between New Zealand and Australia. And you can see from some of the things I'm going to talk about that there's quite a bit of overlap. And partly that's because Sue and I have been working together for more than 10 years. So we talk about what we're doing and we're collaborating. So I was part of the prior NBI bid, and we also had an ARC linkage, which is a way of leveraging funding in Australia, basically with an industry partner, and Plant and Food was an industry partner for that. And then my group's part of this NBI grant that we're talking about today, and Ali, who's a new postdoc working on the program, is going to talk about what we're doing for the bid later on this afternoon. But essentially, you know, we've had a number of people involved. Some are shown in the pictures here, and we've had some really high profile and high impact publications, as well as, I think, some useful outcomes. As you see, some of the things that I've been involved in building in Australia have come out of discussions with Sue and others in New Zealand. One of those things is the marine byproduct CRC, which you may or may not have heard about. So this, Sue showed at the very start a fish, and then the value of the byproduct, the products as what we're calling marine byproducts rather than whole fish. This is sort of the market version of that in Australia. So you've got first generation wild fish, then you've got wild fish in aquaculture, then you've got marine byproducts. So the whole concept of the marine byproduct CRC is to help create this multi-billion-dollar marine byproducts industry in Australia. And that program is 270 million over 10 years. So it's massive. It's just started this year. And it's about 60-something million from the government. And the rest is really from industry partners and so forth. So we have 49 industry partners and essentially 12 research organizations, which are mostly universities. And then we link into a whole bunch of other groups. And to get funded, you really have to have a lot of industry commitment plus integration into other programs such as advanced manufacturing, infrastructure, networks, and growth centers, and so on. So down the bottom, the partners are really not entirely in these areas, but essentially there's a number, say 30 or so interested in biomass production, 17 or more, really, there's more than that, interested in advanced manufacturing. And then there's companies that want products. So there's companies with biomass, there's companies that want to manufacture or have manufacturing capability, and there's ones that want products. And the way that we set our program up is actually in three in 3 programs. Well, there's actually 4. The 4th one is Connect, Educate and Train, which is really around training the next generation of staff to work in industry. But the programs is across the value chain. So marine resources, so it's mostly microalgae and seaweed. And we're not ignoring seafood, but there's actually a blue economy CRC around offshore aquaculture. So we just had to be careful. And there's also food waste CRC. So we had to be careful to have our own space. So we are very interested in seafood industry byproducts, but for the purposes of the application to differentiate ourselves, we primarily focused on seaweed and microalgae. And then program 2 is what we've really been talking about today, but it's my program as well, which is around the manufacturing technology required to make the products, which is program 3. So my program, you can see we're talking very similar things to what we talked about today. By Business Toolbox, which is really this AI stuff that we heard about earlier, and automation, techno-economical modeling is, I guess, one way of referring to it. Then biorefinery concept is critical to the whole thing. That's really making multiple products out of one input material, process automation, modular manufacturing, and then being able to demonstrate that through actual taking biomass and producing products from it, which is, we're calling these blueprints. So I won't get into too much detail, but you can see it's very similar to what we're talking about with the MBI program in terms of technologies. And then at the end of the 10 years, we basically want to have Australia being a major supplier of premium and innovative marine byproducts. So there isn't really a marine byproducts industry at the moment. There's a small one, and New Zealand's actually further ahead than Australia. And most of the CRCs are based on existing large industries, and this is probably the only one that's got funded at this sort of level to create really a new industry. So this is sort of a team. So Katrina's program 1 leader, she's now actually executive director also of IMAS, which is Institute for Marine and Antarctic Sciences. So there's some fairly high profile people here. Rob Capon is at UQ, marine natural products chemist. Wei Zhang is the research lead, and he's really the key driver behind getting this application. Justin's the CEO, so discussions around industry partners and IP and all that lies with him. And there is opportunity for other people to join still. I'm just going to talk really briefly about the funding model. So essentially, there's about 30 of industry partners are core partners, which means they put 100,000 a year minimum. So that means they get 200,000 a year in projects. So that's what this little pie chart's about. So their 100,000 gets doubled up through money from the universities and money from the grant that was awarded. So in Australia, 200,000 gets you pretty much a postdoc with on cost, which is about 120,000 or so, plus consumable and equipment use and all those other things. So it gets you a pretty decent project. That's over 10 years, so it's 200,000 per year. And companies come in different ways, mostly for the whole period, but the projects don't necessarily, one project doesn't necessarily go for that long. It's just to understand what's happening here. But we've leveraged some of this into a large infrastructure grant. There's a lot of money in Australia at the moment for COVID recovery, and also the government is trying to push advanced manufacturing and also get universities to work with industry. So I managed to leverage that to this $10 million state government grant to essentially build a biorefinery, which is similar to what Sue's talking about. And this has come out of Circular Economy Factory. We're calling it the Biofactory. So it's not marine specific, and it was actually funded primarily around food waste. And that's the architectural drawings on the right-hand side. So essentially we're going to have 2 types of systems. One is where you come in, you grind it, you do supercritical or ethanol extraction, and there's the spray dryers and freeze dryers and so forth. And the other one is where you have a water-only process, which is similar to what Sue's pilot plant is, if you see it. Seen that with centrifuges and so forth, which is, it's about 600 square meters, so it's pretty nice. The building's already there, and it's really just fitting it out and buying equipment. So we've got about 4 million to spend on equipment, and RMIT and Monash are part of this as well. So the concept there, pretty clear, I think. You take a biomass like a seaweed, and you break it up into multiple products, so the polysaccharides, the protein, pigments, phenolics, whatever. And then you've got a range of companies that would then take those products. And I guess in terms of the MBA program and also our CRC, I mean, this technology is applicable not just for marine. So you develop the technology. We have this biofactory that Sue's trying to create, and we're putting a similar one here. You can apply that to all sorts of things. So food waste, agricultural waste, rendering, all these are part of our adhesive bid where we've got the infrastructure bid, and even biosolids, which is RMIT's part. So that's working with water utilities and things like that. So, so I think the technology we're trying to create in terms of manufacturing in both programs is not specific to marine necessarily. And that was also reflected in another centre that we got funded a couple of years ago, Green Chemistry and Manufacturing through ARC, which is 4 universities. This is a training centre, but you can see the same sort of concept. We have 3 key areas: advanced sustainable manufacturing, bioprocessing, and products from renewable biomass. And then we have a range of companies in here, and some of these companies are in multiple bids. So Green Ecotech, they have a Waste Master, that's a commercial equipment for food waste processing. So they've got one in our biofactory, so they're part of that, and they're also part of this. And it's really, this equipment's actually in hospitals and other things that they dry the food waste basically for disposal, but we're trying to develop products from that. Manzaris calamari oil, we've been working with them for a long time. We actually built a pilot scale reactor in New Zealand with an engineering company in New Zealand, and that's here now. We're scaling up the calamari production process. Ridley is a large aquaculture feed company. Then Cumming and Haiku are 2 companies on campus. And Haiku is quite interesting. They're actually just joined our marine byproduct CRC, and even though they're textiles and short fibers, now they're looking at marine materials as a source of those. So I think you can link in a range of companies that aren't necessarily focused on marine, especially in the product output area. CRCP is another good way of getting funding. We have one of those in aquaculture with Ridley, and this sort of is one reason they joined our larger CRC. They're still quite sizable bids. And then I think, the biofactory that we've created is available for people to use from anywhere. And also the marine byproduct CRC, even though it's Australian focused, it links pretty closely in with what Sue's doing through this MBA program. And there is, I think, we want to have a network of collaboration internationally. So there's a lot of drivers to that. So marine byproducts are interesting to both, were important economically to both countries, and I think New Zealand's further ahead than Australia. There's funding mechanisms on both sides that Sue and I have taken advantage of, and I think those are becoming larger in some cases. And in Australia in particular, there's increased investment in advanced manufacturing because of the issue around China. China's basically the world's factory, and that's not working out very well at the moment. And then sustainable green automated technology that's reasonably low cost in terms of labour is becoming important if you want to do manufacturing in places like New Zealand, Australia. And then we need to scale up is very expensive, and we really need to share resources because we don't want to build a whole bunch of different facilities. We want to be able to use the small number of facilities for a bunch of projects. So that's me. So thanks.